G'day. We're going to continue our networks videos by talking about something known as the degree of a vertex. So the degree of a vertex is just the number of edge ends that meet at a vertex. So this vertex A here has a degree of 4 because there are 4 edge ends which meet at that vertex. This vertex here, G, has a degree of 1 because there's 1 edge which meets at that vertex. This vertex D has a degree of 2 because you can see there are 2 edge ends which meet at that vertex. Now, we can sometimes refer to these numbers as obviously being even or odd. So this vertex A here has a degree of 4, and 4 being an even number means that this has an even degree. Now this one down here, vertex G, has a degree of 1, which is an odd number, so this has an odd degree. Network traversability is defined as a network that contains a trail that includes all edges once. So this first network over here on the left-hand side is traversable. The trail C, B, D, A, B includes all edges once, and that means that this network is traversable. This network here in the middle is also traversable. That's because it contains a trail that includes all edges once. A, B, A, C, B, D, C. Again, it's a trail, it included all edges once. This network is also considered traversable. The last one here on the right hand side is also traversable. A, D, B, C, D, C, B, and back to A. Now, interestingly enough, this one here on the very right-hand side, we could start at any of the 4 vertices. We didn't necessarily have to start and finish at A. We could have started at D, B, or C. So I've drawn a number of networks, and I'd like you to figure out whether they're traversable or not. So if you'd like, you can pause the video and try and figure that out now. Otherwise, we'll get stuck straight into the worked solutions to these ones here. So you'll see this first one, no matter how I try and approach it, it is simply not traversable. So what I'll do is I'll just put a little cross next to it so we know that that one is not traversable. So the second one along, you'll see that this one is also not traversable. No matter which vertex I start at, it's just simply not possible to trace over all of the edges once, or in more mathematical terms, there's no trail that exists that includes all edges once and once only. So what we'll do now is we'll put a cross next to that one as well. So the third one along is traversable, and funnily enough, we can start at any of the vertices and finish at the same vertex we started at. The next one along is not traversable, so we'll put a little cross next to that one there. So down here on the second row, this one on the left-hand side was also not traversable, and this one too was not traversable. This next one along is traversable. Maybe we'll go back and put a little green tick next to those ones so you know that they are traversable. And now along the bottom row, we'll see that the last 2 are in fact traversable. Now, this large one down the bottom right-hand corner here, this large network or graph, if you know the little trick, it doesn't take you long to figure out whether that particular network is traversable or not. And even though at this stage it seems like traversability is a fun little game to play, it actually plays a bit of a role in identifying graphs, and we'll explore that a little bit later on in the video. So at this point here, I'm now going to let you in on the secret. So for a network to be traversable, it just has to be connected, in which all of these graphs are, but it has to have either 0 or exactly 2 odd vertices. So if you remember back to where we were talking about the even and odd degree of a vertex, in this first one here, we said that this one is not traversable, and that's because it has 1, 2, 3, 4 odd vertices. And remember, it needs to have exactly 2 odd vertices. So again, this is odd because it's got a degree of 1, and 1 is an odd number. This one here is also odd because it has a degree of 3, which is also an odd number. And so the same goes for this one here. It's got a degree of 1, which is an odd number, which means that it also has an odd degree, and so does this one down here. So all 4 vertices have an odd degree, and remember that for a network to be traversable, it has to have 0 or exactly 2 odd vertices. And so that's a good little trick you can use to figure out whether a network is traversable without actually having to get a pen out and then try and trace over the lines. So this one here was not possible to traverse that one, so it's not traversable. This one here was, this one here wasn't, and so on. So you just have to quickly look at the degree of the vertices, and that's a little nice trick to help you cut back some of that working time. This whole idea of traversability actually dates back a few hundred years to the Königsberg Bridge problem. Now the problem is represented down here using this sketch of the town itself. This section here was a piece of land with buildings on it. This piece of land here had buildings and houses on it too. Now the river which ran through town had 2 islands on it. And these sections of land were connected to the islands using these 7 bridges, which I've represented using the yellow lines. Now the story goes that the people who lived in this town tried to find a way to cross over all 7 bridges without having to repeat a bridge. Now as you just saw then, I had to repeat this bridge in order to then cross back over and finish up by going over this last bridge. Now, this gentleman by the name of Carl Gottlieb Euler was a mathematician and a mayor of a nearby town, and he tried for a long time to find a solution to this problem. He called upon Leonhard Euler, and Leonhard worked on this problem for quite a while and then discovered that it was in fact impossible to solve. In order to prove that it was impossible, Leonhard developed a field of mathematics which we now know as graph theory. Now, if we think back to the last slide where we talked about traversability, we can represent this whole Königsberg Bridge problem as a network and soon realize why it's impossible to solve. Now we know that no network is traversable if it has more than 2 vertices with an odd degree. And if we represent this town here using this network, these vertices representing the pieces of land and these edges representing the 7 bridges, you can see that if we count the number of vertices which have an odd degree, there is 1, 2, 3. And as we now know, any network which has more than 2 odd vertices is not traversable. Moving on to Eulerian Trails graphs and semi-Eulerian graphs. Eulerian trails are a trail interconnected graph that visit every edge once. An Eulerian graph is a graph that contains an Eulerian circuit, or in other words, a trail that includes every edge once and starts and finishes at the same vertex. So I've drawn 2 examples here of Eulerian graphs, and we can call these Eulerian graphs because they contain an Eulerian circuit. So this first graph here, for example, has an Eulerian circuit, and that can be represented here as A, B, C, D, E, F, C, G, and then back to A. So if we write that down, it would look something like this. A, B, C, D, E, F, C, G, and then back to A. Of course, it's Eulerian because it includes every edge once and once only, and it starts and finishes at the same vertex A. Now, if we have a look at the next graph over here, you can see that this is also Eulerian. We can start at this vertex B, for example, and we can move around this curved edge to D, up to C, up to B, back down to D, up to A, and finishing at B. Again, this graph contains an Eulerian trail, and so we can classify this graph as an Eulerian graph. So a solution which would help us to show that this is an Eulerian graph would be to list the trail B, D, C, B, D, A, B. And a quick little shortcut to help you to identify whether a graph is Eulerian or not is to pay attention to this little note here. So in an Eulerian graph, every vertex has to have an even degree. And if you need to list the trail or the closed trail, remembering that they can be called a circuit, if you need to list that, you can start and finish at any vertex, provided again that all of the vertices are even. Now moving on to semi-Eulerian graphs, they're a graph that contain an open Eulerian trail. So in other words, a trail that includes all edges once and starts and finishes at different vertices. In this example down here, I'm now going to show you this open trail that exists that includes all edges once and once only, which helps us to define this graph here as being semi-Eulerian. So if I pick up my pen and I write down A, B, A, C, B, you'll notice that this time I haven't started and finished at the same vertex. I started at vertex A and finished at vertex B. So you can see that I've written a trail that includes all edges once, and it started and finished at different vertices. So if I trace over those edges, so starting at vertex A over to vertex B, just as I've written here, so A, B, back to A, down to C, and finishing at B. So it's an open trail. It included all edges once and once only, and so that's why we can classify this graph here as being semi-Eulerian. Now we look at the last example over here, and before I even get started, I know that this is semi-Eulerian because if I look at this vertex B and I look at this vertex D, they both have a degree of 3, which means that both of these have an odd degree. The other two have an even degree. Now, a little note here, semi-Eulerian graphs have exactly 2 vertices with an odd degree. This one here had exactly 2 vertices with an odd degree, so that's why I knew straight away that it was semi-Eulerian without having to list the trail. Now, another little fun fact is that the trail must begin at one of these odd degree vertices and finish at the other. So don't try and start your trail at an even vertex because it won't work. Now, this one here, you'll notice that I started at A, which funnily enough has an odd degree, and I finished at B, which also has an odd degree. So with this one over here, you can tell that I'm going to have to start at B or D because they're the 2 vertices with the odd degree. So if I wanted to list a trail which would help us to show that this was a semi-Eulerian graph, I could list something like this: B, C, D, B, A, D. And so if I take out my little highlighter pen pointer thing, and we follow that trail, we go from B to C to D, up to B, over to A, and back down to D. So it's an open trail. It included all edges once and once only. And so that's why we know that this graph here is semi-Eulerian. Moving on to Hamiltonian paths, graphs, and semi-Hamiltonian graphs. A Hamiltonian path is a path that visits every vertex once. So the only possible exception to this is if you start and finish at the same vertex. Then, of course, we have repeated a vertex, but that is the only exception. Now, note the difference between this and Eulerian is that with Hamiltonian graphs, we just need to find a path that visits every vertex once. There's no need to worry about visiting every edge or including every edge in our path. It just simply needs to be every vertex. Now, a Hamiltonian graph is a connected graph that contains a Hamiltonian cycle. So remember, a cycle is a special kind of path that starts and finishes at the same vertex. Now, a Hamiltonian cycle is a path that starts and finishes at the same vertex and visits every vertex once. So an example of just a cycle would be A to B and back to A. But now we're looking at a Hamiltonian cycle, which has to visit every vertex. So we can't just visit A and B, we now need to visit C. And so you can see that there is a path which visits A, B, C, and can finish at A again. And because that exists in this graph here, this graph can be described as being Hamiltonian. Now, funnily enough, you would have seen this graph in the last slide where I talked about this exact same graph being semi-Eulerian, and that's because it contained an open trail. Now, in this case, this graph also contains a closed path, otherwise known as a cycle, and because this path visited every vertex, it's a Hamiltonian cycle, which is what made this graph Hamiltonian. So yes, it is possible for a graph to be classified as Hamiltonian, and it can also be classified as semi-Eulerian. So I'll just write down that path and then we'll move on to the next example. So the path which helped us to show that this was Hamiltonian was A, B, C, and then back to A again. Now we'll look at the next example over here. So this is Hamiltonian, and so the path needs to be closed in aka a cycle to prove that this is Hamiltonian. We can start at, say, E this time, and we can go from E to B to C to D to A and back to E. So again, I didn't visit every edge once because we're not interested in all the edges at the moment. Hamiltonian graphs are graphs which contain a Hamiltonian cycle, which is a path that includes all vertices once, with the exception, of course, the one that you start and finish at. So now let's write that cycle down. I wrote E, B, C, D, A, and back to E again. And moving down to the bottom now, where we look at semi-Hamiltonian graphs. So these two, this one here is semi-Hamiltonian. We'll look at this one here in a moment, but for now, this one over here is semi-Hamiltonian, and that's because it's a connected graph. It contains an open Hamiltonian path. So, in other words, a path that starts and finishes at different vertices and visits every vertex once. So an example of that path would be D, E, F, C, G, A, and B. So let's write that one down now. D, E, F, C, G, A, B. Now in this case, there is no option to return to the vertex that we started at. So we started here at D, and if once we get to B, the only way we could get back to D to complete the cycle would be if we had to repeat this vertex C. Now remember, paths, you cannot repeat a vertex when you're listing a path, okay? Only trails can repeat vertices. So there is no possible way of getting back to the same vertex that I started at, and so it has to remain an open path. And because there is an open path which includes all vertices once and once only, we can then classify this graph as being semi-Hamiltonian. Now this one down the bottom right hand corner I simply wrote down here because I thought it would be an interesting one to finish on. And so we spoke about sometimes graphs can have more than one classification, because this one here you would have seen on the last slide as well, because it was classified as Eulerian. So this one can be Eulerian and semi-Hamiltonian. This one down here in the bottom right hand corner actually cannot be classified as Hamiltonian or Eulerian. And that's because there is no trail that could exist that includes all edges once. And there is no path which can visit every vertex once. We would have to repeat vertices to visit every vertex. And so in this case, this graph or network down here, the bottom right hand corner, is neither Hamiltonian nor Eulerian. Now I'd like you to summarise the notes from this video and complete exercise 5D from your Sadler Unit 3 textbook. Have a sensational day.